Let's talk about another problem and we'll do it both ways. Here are four numbers in a population that have a sum of 20 and of course a mean of 5. I can start off doing it the computational way as we discussed before. I've got the sum of all the values squared at 120, or I add them all up and then square. 20 squared is 400. Plug them into that really direct formula there. 120 minus 400 over 4. 120 minus 100 is 20. Fair enough. I could do it the easier way. In this case, the reason I might call it the easier way is because the mean is rounded. I subtract the mean from each number. Now the mean here is 5. 8 plus 6 plus 4 plus 2 is 20 divided by 4 is 5. And you can see I've got the column where it's every value minus the number. That's the deviation. And of course the sum of those deviations is 0. Then square everything. And I get the sum of the square deviations at 20, which was precisely the same as it was in the previous problem. So that worked out well. I like confirming that. And then I could go on to calculate the standard deviation. Here's the variance, the sum of the squares over capital N. 20 over 4 is 5, and then I just take the square root of 5 in order to get the standard deviation. So that's pretty cakey. But if you'll indulge me, what I'd like to do is show an array of numbers whose mean is also 5, but are more spread out. And of course, we'd expect a bigger standard deviation. Look at these numbers: 15, 7, 3, and negative 5. Their sum is 20. And of course, their mean is 5, just the same. I could undergo the computational formula, and of course, the numbers are a lot bigger this time. They're just a little harder to deal with. The sum of all the values squared, as you can see, I squared 15 and got 225, 7 and got 49, 3 and got 9, negative 5 got 25. The sum of all those values squared, 308. And then I took 20 squared is 400. And you can see my calculation here, 308 minus 400 over 4. And now I'm getting a much larger sum of squares of 208. Well, fair enough. May I do it the other way? Sure. Here we go. I just subtracted that mean of 5 from everything. And of course, I got 15 minus 5 is 10. 7 minus 5 is 2. The sum of all the deviations is 0. And then I squared all of those deviations. I got a much larger number, again, 208. So because the numbers are more spread out, I got a much larger sum of the squared deviations from the mean, as might be expected. They're a heck of a lot larger, and therefore the sum of squares, the squared deviations from the mean, would be expected to be larger. Will the standard deviation be larger? Well, sure. Look, here's my variance at 52. I got that huge sum of squares at 208 divided by 4. That's 52, and of course the square root of that, using a calculator, of course, 7.21. So as expected, when I had a large, or I should say a group of numbers that have a lot of spread between them, although they have a mean of 5, there's a lot of spread here. Sure enough, the standard deviation is 7.21. Conversely, when I had these numbers, you can see there's considerably less spread. They only go from 8 to 2. And from 8 to 2, that's roughly a range of 6, or you might strictly say 7, 8.5 to 1.5, doesn't matter. But of course, the standard deviation was a lot smaller at 2.24. So I put these problems in consecutive order here, even though they have the same mean, to demonstrate that the standard deviation will be larger with greater spread. Here's a standard deviation of 2.24. With these large numbers, or I should say these numbers that have the same mean but have a larger spread, they have the standard deviation that, of course, is higher. So although we really haven't put the standard deviation in context yet, like what it actually does and how it relates to tables that we'll use, I really appreciate the ability to at least witness that when I have an array of numbers that's more spread out, of course, the standard deviation is appreciably larger.